Hi, my name is Patrick O'Neill. I'm a PhD student at Texas A&M, and I work with Dr. Sunil Chirioth. And today I will be presenting some work that we have been doing to use machine learning techniques to identify irradiated fuel attributes. So previous work at A&M was able to produce a nuclear forensics methodology capable of finding the reactor of origin, burnup, and time-sensitive radiation of separated plutonium, and it's a very good methodology. However, we noticed that there is a weakness in that it is only able to attribute plutonium that is from one reactor type with one burnup and one time sensitive radiation. So if you have any mixed samples, whether that's mixing plutonium from two different reactor sources, or maybe plutonium from two different batches from the same reactor that have different burnups and time sensitive irradiations, uh, the methodology would be incapable of providing meaningful information on that sample. So that's a weakness that we wanted to improve upon to make a more robust methodology. And so here's some work that we've been doing to try and do that. So why is this relevant to MTV and the MTV sponsors? The ability to identify a plutonium source's origin can strengthen our ability to investigate both declared activities and clandestine activities of foreign nuclear fuel cycles. So one way that this could be impactful is verifying declared activities at facilities that are under safeguards. So if you have an operator and they say we have uh, this material and it was produced in this reactor and it was in that reactor for this long, and here's how long it's been since it was in that reactor. If we were able to take a very small sample of that plutonium and verify that, that's a very powerful capability to have. Additionally, if we found a plutonium sample that we had no idea what its origins were, and maybe interdicted at a border crossing or a situation like that, and we were able to point out maybe where it was from, that's very powerful information and could aid decision makers. And also, if it was known that this capability existed, that could act as a deterrent to nuclear smuggling. So here is kind of how that previous methodology that I talked about worked. It used a maximum likelihood method. So the main predictors of this methodology are intra-elemental isotopic ratio sets. You can see that in the ratio set box of the graphic on the left of the slide. And we created a simulated or a reference data library from simulated data produced using MCMP over a burnup range and a TSI range, and for different reactor types that we were interested in. And so we created this matrix of ratio sets at different burnups, time sensitive radiations, and then we had a bunch of those matrices, one for each of the reactor types that we're interested in. And if you had an experimental sample and you found all of these intra-elemental isotopic ratios, then you could compare against every point in all of those reference matrices, and whichever most closely matched the experimental ratio set would indicate the attributes that you're interested in. So the burnup, the time sensitive radiation, and the reactor of origin. So we want to keep using that reference library that was kind of in the first step, and those intra-elemental isotopic ratios. But instead of doing the maximum likelihood calculation of comparing against every point in the library, we want to use that data to produce models that are trained using machine learning to attribute the plutonium samples. So to do this, we first needed a training data set. So we randomly sampled the 3 attributes that we're interested in finding over the ranges of interest, and then we interpolated using those 3 attributes to find what isotopic ratios would match those 3 attributes from our simulated data library. And then we trained some models. We trained a reactor classifier, reactor type classifier, and we used 7 ratios to do that. And then we trained a set of burnup models using regression models. and we train those with a different set of 7 ratios. It's a very similar set, but there's a slight difference. And then we actually found, because we know the reactor type, or we're predicting the reactor type and predicting the burnup, we can analytically solve for the time-sensitive radiation. So a little bit more about those models. The reactor classifier is a support vector machine classifier. It uses a qubit kernel and the 7 ratios you can see on the left. I highlighted the cesium ratio because the burnup models, as I said, have a slightly different set of 7 ratios. It's the same 6 ratios and then a different cesium ratio. So I just wanted to highlight that fact. Right now, we're capable of discerning between 5 different reactor types: a PWR, PHWR, FBR, HIFER, and MER. The PWR, PHWR, and FBR are kind of generic versions of those reactor types. The HIFER and MER are a little bit more specific. Those are 2 research reactors. HIFER is at Oak Ridge, and MER is at the University of Missouri. And the reason we have HIFER and MER in that set is we have some validation data that we have from doing irradiation experiments at those 2 facilities. So we wanted to test our models using that validation data. We needed HIFER and MER in the reactor classifier. Right now, we're achieving an accuracy of 99.8%, which we're very pleased with. It's very high. And I think kind of a check on that is to look at where our model is failing, and it's only failing in the very low burnup range, which makes sense because some of these isotopic, some of these ratios, the isotopes in them need to build up as the reactor operates, depending on what kind of parent isotopes it has that need to decay, or things like that. And also, this isn't an operational concern, as a potential weakness of this approach, because these burnup ranges are so low that it wouldn't be feasible for a proliferator to even want to burn a fuel to such a comically low amount. It wouldn't be useful for them. So talking about the regression models that we use to quantify burnup, we use Gaussian process regression models with an exponential kernel, and we have 1 model for each of our reactor types. They're capable of discriminating burnups in a range of 0 to 5 gigawatt days per MTU. And again, it uses 7 ratios. 6 of those are the same. The only difference is the cesium ratio from the classifier set. And you can see what kind of errors we have associated with these reactor prediction models. We have some root mean squared errors in the table in the kind of the center bottom of the slide, and we're happy with that performance. And to give you a little bit better idea of how we're doing our TSI quantification, we're using the cesium 134 to 137 ratio. And basically, once we've predicted a reactor type and predicted a burnup, we can go back to our reference library of simulated data and find what that ratio would have looked like at discharge, so a TSI of 0. And then by, because we now have the ratio at t equals 0 and the ratio at now, we can then use the decay equations to find how much time has elapsed. And so right now, we can quantify for a range of 0 to 5,000 days. That's just because of how long we've kind of calculated our library to, but we could, decay is very easy to calculate, and we can really expand that as we move forward. So I talked about how we have some validation data, and here is how the models performed with that validation data for both HIFER and MER. So for both of those tables, we have what was measured, we have what was predicted by the maximum likelihood, and what is predicted by the new machine learning approach. And important to note, we're not looking to best the maximum likelihood in this case. We were satisfied with the maximum likelihood's performance for pure samples. And so the machine learning just kind of needs to replicate that for this step in the process, because we believe that the machine learning will be able to handle more complex samples than the maximum likelihood was. And we achieved that. To that end, we're happy with the machine learning's model performance for both of these validation datas, and that's a big sign that we can move forward. So one thing we have kind of started to do is use some feature selection techniques to inform maybe some changes that we might want to implement concerning which isotopic ratios we use. So by using feature selection techniques, we can find which ratios are contributing the most to our predictions. And this can save time in training. The less predictors you have, the less training time it will take. And then also it can save lab time because one of these ratios might be additional radiation measurements or radiochemistry measurements, time on the mass spec. Maybe it's an additional column separation that we don't have to do. So it can be very powerful to find exactly which ratios are contributing to exactly which attributes and maybe reduce our ratio set that we care about. So we're using a minimum redundancy, maximum relevance approach for the reactor classifier set, and you can see that on the right of this slide. The big takeaway is that the cesium ratio and the barium ratio, as well as the Pu 240 to 239 ratio, are proving to be the most important in discriminating between the reactor types. And then we also are using a neighborhood component analysis for our burnup regression models, which we can see on this slide. I've included the PWR, the FBR, and the HIFER NCA analyses just to show how different ratios might be more important based on what neutron energy spectra the reactor has. So the fast reactor, the FBR in the center there, the samarium 152 to 149 has the most weight in that of those features, whereas in the PWR, which is a thermal reactor, the barium is more important. So both the MR and the NCA are not, the end all be all. Just because one component doesn't seem to have as much weight in these doesn't necessarily mean I'm automatically going to cut it. You really can't tell exactly what effect these have until you actually start training some models with different subsets of the isotopic ratios and seeing how your performance maybe changes. So these analyses are just sort of a guide. So what is the expected impact of this project? Kind of like I talked about before in the motivation, enhancing our capabilities to monitor foreign nuclear fuel cycles, both with declared safeguards monitoring, looking at material declaration verification, and also maybe improving our ability to get information from environmental sample analyses. And it can also be applied in the nuclear security arena to attribute material that isn't under regulatory control. How has MTV impacted my work? First and foremost, I've had some collaborations that have been excellent with national labs. I have an ongoing one with Lawrence Livermore, and I'm starting one with Sandia, and then those are both facilitated by MTV, so I'm very grateful for those. I was also able to present this work at the Next Gen AI for Proliferation Detection Domain Aware Methods workshop, which was recently occurred, and that was a great opportunity. I learned a lot about machine learning and how it's being used in the proliferation detection world, and that was really excellent. We're building human capacity of using machine learning in nuclear forensics, which is me. I mean, I didn't know anything about machine learning until I started this project and with MTV, and it's been a really excellent learning experience, and that's an impact, right? We're informing what kind of radiochemistry work occurs at Texas A&M. And we're also getting some interdisciplinary collaboration between people like myself who maybe have a reactor physics background with radiochemists and data scientists. So that's really awesome. Some next steps is we want to augment our classifier to attribute spoofed plutonium samples, as well as train a regression model to find the mixture characteristics of that spoofed plutonium. And we also want to produce more validation